Alright, so minimum reinforcement. We have that in reinforced concrete. It's handled a little bit differently in pre-stressed concrete, particularly for the bonded tendons. So I've pulled some sections out of the code here in the 9.6.2 area, and you can see we've got two pieces here. We've got minimal flexural reinforcement for pre-stressed beams is this whole section. Bonded pre-stressed reinforcement, we have to have a total quantity of steel, both reinforced standard reinforced and pre-stressed type steel, develop a factored load of at least 1.2 times the cracking load calculated on the basis of the modulus of rupture. That's the 7.5 squared F prime C. That's for the bonded pre-stress. If we're doing unbonded tendons, the minimum is this equation, which is based on 0.4% of the area of kind of the tension region. So let me walk through this and summarize these. So for bonded pre-stress, what we essentially want to make sure is that we have enough capacity to get to cracking and beyond. So if I have a really heavy section, design section, really strong sections, I might get to the point where I have failure before it cracks, and that's going to look like a pretty explosive failure rather than having the cracking first, so we know that that's not something we want to see. So the best way the code has found to ensure this for pre-stressed beams is to say, okay, you need to have at least Vmn, so that's your capacity, has to be at least 1.2 times moment cracking, and you know how to calculate moment cracking. It comes from modulus of rupture. Okay, so you have to have this. The other option you have is here for bonded pre-stress, and that is that if they have both flexural and shear strength, so shear capacity and flexural capacity are both twice what you calculate that you need. Okay, so this is basically if it's so over-designed that you have 2 times both those capacities, which I'm not sure why you would do that, so this doesn't tend to be one that applies, but in this case they're like, you know, that's such a high factor of safety that we're not going to worry about that explosive failure because you should never reach it. Now, for unbonded pre-stress, they handle this a little bit differently, and they base a minimum amount of bonded steel in this equation, the minimum area of steel that you need, and typically this required steel is not going to be pre-stress, it's just going to be rebar. But any kind of steel you need to have at least 0.004 times area sub CT, and CT is this area. If this is compression and this is tension, it's between the centroid and the extreme tension face. So you calculate that concrete area, and then you multiply by 0.004, and you provide that much reinforcing bar in there. A lot of this stems from the fact that in an unbonded tendon it can be a kind of a sudden failure if you lose an anchorage or something like that. It also, you know, not that the rebar would necessarily help that, but they would help bridge cracks. So with an unbonded tendon, it acts more like arch type behavior than it does what we're used to, where the whole section of the concrete and steel strains remain the same. So without the bonding, it looks a lot different, and you tend to have wider space, larger cracks, and that's why the FPS equation is different as well. So we put in some bonded reinforcement to try to bridge those cracks and make everything not completely relying on the unbonded tendons. This is something that actually people in the post-tensioning world argue a bit, because these are post-tensioned, these unbonded ones. Whether that's really needed or not, but that is what is in the code, and so that is what we follow.